So we start with the first technical session. The topic of this session will be interactive theorem proving. And the first presentation will be given by Matt Griffin. So Matt, could you share your slides?
Sure.
So Matt will talk about verifying secure speculation in Isabelle HOL. So Matt, please, the floor is yours.
Thank you. Welcome, and thank you all for being here today. It's a bit unnerving going first, but hopefully I can provide a great first talk. My name is Matt Griffin. I'm a PhD student at the University of Surrey in the UK. I spend most of my research time convincing theorem provers like Isabelle HOL to verify complex hyperproperties. One of these hyperproperties is the novel trace property dependent observational determinism, or TPOD. TPOD attempts to address a major issue concerning both software and hardware researchers, and that is, how can we speculate securely? First, let us understand what this presentation aims to accomplish. We'll need a definition of secure speculation and why it's important. To verify secure speculation, we'll need to characterize it with operational semantics. Moreover, these operational semantics will need to be applied to real-world programs to show if they're vulnerable or secure. Lastly, and the trickiest part, will be whether or not we can mechanize this verification. So secure speculation remains an active area of research since the discovery of Spectre and Meltdown in 2018. As late as April this year, vulnerabilities have been found which bypass the security systems, and these security systems were employed to mitigate Spectre. So this is by no means a cut and dry vulnerability. I've mentioned secure speculation frequently, but what is it? Well, secure speculation is the absence of speculative execution attacks. So what is a speculative execution attack then? Speculative execution attacks are a class of transient execution vulnerabilities encapsulating Meltdown and Spectre, which specifically target speculative execution on modern microprocessors. The general formula for this attack follows a pattern on the slides here. So first, an attacker will mistrain the processor's branch predictor, the logic unit which decides when speculative execution should occur. The adversary will then invoke some trusted code with inputs chosen by themselves. Through mistraining in step one, the attacker can trigger misspeculation, and then the adversary or the attacker can extract secrets from some side channel. Our research really focuses on stage 3 of the above attack, mitigating misspeculation. We exclusively look at variant 1 of Spectre, the bounce check bypass, which targets the branch predictor's pattern history table to try and trick the processor into misspeculating. We must reason at the assembly level, as compilers may optimize OAR mitigations in high-level languages, and we attempt to ensure the correct placement of speculative fences in assembly programs. The speculative fences are instructions which terminate all speculation, so whether that's safe or unsafe, and Intel has the L fence and ARM has CSDB. So Paul Cocker identified a set of victim functions in his research into MSVC's mitigation of Spectre. These are effectively permutations of the vulnerable code identified in the original Spectre paper. I've sort of highlighted a subset here of some of the examples, just to give you a feel for the type of program we're working with. So what do we need to ensure secure speculation? Cheng et al. Defines operational semantics for secure speculation and TPOD, a hyperproperty capable of capturing violations of secure speculation. Our work takes TPOD and the operational semantics and encodes it in Isabelle HOL. We've simplified the existing semantics presented by Cheng et al. And reduced the state space explosion associated with verifying this property. We've provided high-level theorems to discharge the trivial proof cases, and we've verified the presence and absence of vulnerabilities in a set of examples. Finally, we've formulated transition tools for converting C programs into Isabelle HOL theories. So, as seen on the slides, the translation process to prove small examples of C code secure proceeds as follows. In a similar way to Chung et al., we first compile the C source code with MSVC, and this resulting binary is translated into an assembly intermediary representation known as BIL, and we do this using the binary analysis platform, or BAP. We use our tool to translate these BIL files into Isabelle HOL, which can prove if they are secure or insecure using our framework. Each step can be executed individually, so this allows for corrections to be made to insecure examples. We'll analyze the first victim function in detail to see exactly what goes wrong. So on the right side of this slide, I've given the C code for the first example, and on the left is the assembly language, written in an intermediary form. Before executing this function, the attacker would train the branch predictor by invoking functions with an input of x that are less than the size of array 1. This will pass the bounds check on line 2 of the C code. The branch predictor's pattern history table will build up a true prediction for this condition. After sufficiently training the branch predictor, the adversary would invoke the code with a malicious input larger than the size of array 1. It's good to see that the bounds check will fail under regular execution, but under speculative execution, the bounds check may pass. This happens due to the repeated training of the branch predictor to think that this is the most likely outcome for this branch. By executing the instructions in the second block speculatively, with an input larger than the size of array 1, we make an unbounded read from memory, and this enters the speculative state at line 1C, 1C. This is fine as a speculative state is not observable. It never leaves the processor. We cannot observe this unbounded read until instruction 1C60, where a read from memory forces a value in the accumulator register into the memory's cache or the processor's cache. We assume that the extraction from the cache is trivial, and the adversary can obtain the value read on line 1C, 1C. We also assume that the mistraining the branch predictor is trivial too. So Paul Cocker's research focused around testing and speculative mitigations of MSVC, and as such, he found that Microsoft's compiler places a speculative fence at address 1BB8, forcing the branch predictor to resolve any speculative execution at the start of this block. Therefore, we never misspeculate the instructions 1C, 1C, and 1C60, meaning we never invite an unbounded read into the speculative state or the microarchitecture state. So the program is secure. As mentioned previously, though, the vulnerability really only occurs at 1C60. MSVC has placed this spec fence at the start of the trusted block. Preventing instructions over these non-vulnerable instructions, it sort of invites poor performance. We must not forget that speculative execution is correct behavior, and it greatly improves the performance of modern microprocessors. We can achieve the same security with this revised solution, which places a spec fence right before the vulnerable instruction at 1C60. This permits an unbounded read to the speculative state, but prevents the value from entering the microarchitectural state. And since the speculative state is discarded on resolution, the vulnerability does not occur. MSVC was only able to identify vulnerabilities in 2 of the 15 functions presented by Paul Cocker. Therefore, we shouldn't trust the compiler. Really, we need to ensure the programs are secure ourselves. We present the operational semantics over machine state S, which consists of the program memory, pi, the register state delta, the data memory state mu, the program counter PC, a trace of the instructions and data memory accessed, omega, the branch predictor, beta, and finally the speculation level, which is just n. Register state, data memory state, and program counter are all functions over the current speculation level. This enables the differentiation between the speculative and architectural states. Here we show the semantics involving true evaluation of a condition on the branch instruction, the uninterpreted misread predicate in this these rules determines if the process will begin to misspeculate, and there are equivalents for false branches too. Here we present an interesting selection of the transition rules. These include the spec fence instruction, which resolves all speculation back to the architectural state, as well as resolve, which models the occurrence that the branch predictor realizes it has mispredicted the outcome of a branch and resolves the misspeculation. This simply reduces the speculation level, discarding the current speculative state. And this can occur at any time the system is misspeculating. The remaining inference rules for load store, register update, go to, and no operation instructions are given in the paper. We define the capabilities of the adversary as follows. We consider trusted execution, i.e. that of a kernel, to be the execution of any instruction whose program address is not in this trusted set. We constrain jumps to a program address in the trusted set to target a trusted entry point. This prevents a jump past speculative barriers we may place in trusted code, which would otherwise prevent the spec fences from working. We define a secret set of data addresses, which we'd aim to protect. And finally, we ensure that loads and stores outside of trusted execution are constrained to memory addresses in the adversary readable and writable sets, because otherwise the adversary could simply read secrets from memory. Traditional safety and liveness properties are generalized over a single trace. Properties involving speculative execution generally require a more general class of properties. We call these hyperproperties, which are formalized over sets of traces. We require a 4-trace hyperproperty over traces pi1 to 4. This consists of deterministic traces which do not speculate, pi1 and 2. The non-deterministic traces which can speculate, pi3 and 4. We pair these deterministic and non-deterministic traces together, pi1 and 3 as a pair, and pi2 and 4 as a pair. We aim to identify if there's an observable, according to the adversary, difference between the speculative states in traces pi3 and 4. So here's the definition of T-pod. At line 1, we see that pi1 and 2 are traces with no misprediction, and hence no speculation, whilst pi3 and 4 are traces with misprediction. We express the trace property T as for all states in the trace pi, this state's not mispredicting. All 4 traces execute the same sequence of non-trusted instructions, and trace pairs execute the same sequence of trusted instructions. There's never an observed difference between traces pi1 and 2, while initially there is never an observable difference between traces pi3 and 4. Under these assumptions, we must show that there is never an observable difference between pi3 and pi4. So we'll move on to the mechanization. We build state transitions with Hoare-style proof rules. By extending the definition of a state transition to 2 and then 4 states, we can reduce the verification space by finding strong invariance between the states. We also discharge trivial programs from a given state in a trace when some condition is not met. For example, if T-pod currently holds and we're not speculating and there's no more branches left in the set of instructions, we can quite easily infer that T-pod will hold. This effectively leaves us with less to prove manually. So I'd like to give a quick demonstration of the tool. It's pre-recorded, so hopefully I can get the audio to play through Zoom.
With our source code, EX01. We first start with our source code, EX01.c. If we look at this file, it contains a definition for the victim function with the bounds check, the trusted code. Array 2 is read from the value of array 1 with some processing. During compilation, this results in the following x86 assembly. We compile our source using the tool, which invokes MSVC with the correct parameters for speculative mitigations. This generates an exe. We can translate this exe to BIL using the binary analysis platform. If we take a look at the build file, we can see the assembly in an intermediary language. This contains the branch and condition to mispredict, the out-of-bounds read in the speculative state, and the out-of-bounds read in the microarchitectural state. There's a lot of extra instructions in this file, but we'll trim out those in the next step. We now use the tool to convert this bill to Isabelle theories. Let's look at the Isabelle file. We defined invariants and constants for the program, as well as the program memory, with a mispredicting branch, the out-of-bounds read in the speculative state, and the out-of-bounds value brought into the microarchitectural state. We use the constants and invariants to create an initial predicate over a single state. We then extend this to 2 and then 4 states. We prove that the initial 4 states are well formed, satisfy the violation constraints, and are low equivalent. We define an initial execution and prove that that initial execution is a valid execution. We then prove that the initial execution is low equivalent. These proofs are stepwise. First, we define the next 4 states the system transitions to. In this case, this is from the initial 4 states. Then we prove that the system transitions to the states we just saw in the step 1 predicate. We now prove that step 1 is low equivalent, and an execution to step 1 is a valid execution. We also prove that that execution is low equivalent. As we know, the program is insecure. As such, this theory should identify the vulnerability. We follow this stepwise process to build the proof up to a conclusion. Here we see that low equivalence, for example, 1 has failed at step 15. As low equivalence has failed at step 15, we've identified the vulnerable instruction. This is simply the instruction at position 15 in the program memory shown earlier. Right, so as we know the vulnerability is here, we can place a spec fence directly above that. As the spec fence is before the vulnerability, it should ensure secure speculation holds. Let's try proving our corrected bill. The tool has generated a new Isabelle theory. You can see the spec fence preventing vulnerability in the program memory. So let's jump to the last step in our proof. Here we give the next state if we execute the spec fence instruction, and as we are speculating, the next state if the branch predictor resolves. As this is a stepwise proof, we need to prove that we transition from the last step into the next step, which in this case is 14. We can see here that the instruction being executed is spec fence, which is what we expect. Here that we can see that step 14 is low equivalent. Here we use high-level lemmas to discharge any further execution from step 14. This is a case after a resolve, as well as executing the spec fence instruction. This is enough to convince ourselves that the program satisfies TPOD, and all speculation is secure.
Right. Thanks for watching that. Right. To conclude, I've covered the importance of secure speculation, discussed the mitigations for specific variants of Spectre, and that's namely the bounds check bypass, the variant 1. I've discussed how compiler solutions are suboptimal or incorrect, and shown how we've used Isabelle HOL to encode TPOD. I've introduced deductive HOL logic style encodings similar to what we see in the self-fault proofs, and simplified the operational semantics proposed by Cheng et al. And introduced well-formedness to reduce state space verification space. Finally, demonstrated the automatic translation tool from C to Isabelle HOL. So in future work, we aim to generalize TPOD and express it in bounded deducibility security. We also wish to improve the versatility of the mechanized tool, practical to use in any setting. Right now, it's quite, I think, as you could see from the vulnerable example, the way of proving a program is insecure at the moment is a sort of failed low equivalence. I'd like that to be a proper proof that it's good. Right, thank you. Is there any questions?
Thank you. A big applause for everybody. If people have questions, they can put them in the chat. And I already see one appearing. Paula was prepared. So she says, so this is a question by Paula Herber. She says, thanks for this talk, very interesting work. One question, how many lines of proof code do you get per line of code approximately?
So the proofs are very verbose. There will be a lot of lines of proof code for each line of code. I haven't got the exact numbers, and it's not something I've actually considered, but I would estimate it to be about, for every one line, probably about 100 to 120. And that's why the tool is quite important, even in the cases where it can't exactly find the proof. Again, with the failed example one's quite simple, but some of the more complex examples involving loops, it doesn't always, you may have to run it with the exhaustive option I sort of showed, and that basically does a lot of the proof writing for you, and then you can just go in and fix any slight errors that might be there.
But who would
Thank you very much.
I
just said thank you, sorry.
No, that's okay. I didn't know you could talk. So I wanted to ask a follow-up question actually on what Paula was asking about who are your intended tool users, because what you showed to us, I mean, it looks still that you really have to understand the Isabelle formalization. Is that how you foresee how this would be used, or do you have other plans? Well,
that would be the plan for our future work, to sort of improve the utility and accessibility of the tool, because you are right to say that the understanding of Isabelle is quite important to using this tool at the moment. As for intended audience, like developers of compilers and secure compilers, I don't expect this to ever be, or to really be included in the compilation process, but this would be something that potentially you could use to test that a compiler's mitigation. So like the mitigations in the MSVC, for example, actually do produce code that is secure. Yeah. Okay, thanks. And I have one, that's the last question, I think, given the time. There's a question by Oyandrila Dobe, who says, great talk. Could you elaborate on how you reduce the state space a little more? Sure. Actually, yeah, that's not something I went into much depth on in the presentation. We cover it a lot in the paper. So by stepping, if we were to consider the state separately, so I think, slide. Yeah, so when we encode the semantics, we build up to 4 state transitions from a single transition. So for a single transition in the trace, we go to 2 and then 4. This allows us to sort of find invariants in the traces, things that aren't possible and are possible. And that quite greatly reduces the number of combinations we kind of have to look at. There's also a lot we do for, we test states, or we'll test states to see if they have reached or if they satisfy a predicate that identifies whether or not this, basically in the same way we discharge trivial programs, we can discharge programs that are going to be insecure. So we can find points of insecurity or programs that are insecure early. I can discuss that more over email. So I think we're out of time. Yeah.
So I think that would be very nice. Then I would like to thank you once more for this interesting talk. And we move on to the next speaker. The next presentation will be given by Conrad Watt.